In this video, I'm going to talk about the geometrical meaning of the Ricci Curvature tensor and the Ricci scalar. Both of these are derived from the Riemann curvature tensor, which I talked about in videos 22 and 23. So check the description for links to those videos if you haven't seen them. This video is about being able to get a visual intuition for what the Ricci tensor means. I'm going to cover the more algebraic mathematical properties of the Ricci tensor in a later video, Tensor Calculus number 26. So you can watch that video as well if you want to learn more. So both the Ricci tensor and Ricci scalar can be thought of as summarizing the Riemann tensor that we learned about before. The Ricci tensor tracks volume changes along geodesics. So as we can see in this picture, if we take this rabbit and make all its points travel along geodesic curves, it actually shrinks in size. So the Ricci tensor tells us about how volumes grow or shrink as they move along geodesics. And there are two geometrical approaches to understanding the Ricci tensor that I'll discuss: sectional curvature and the volume element derivative. Also, the Ricci scalar is a number that's used to compare the volume of a ball in curved space to the volume of a ball of the same radius in flat space. So, as I said, the Ricci tensor is the thing that helps us keep track of volume changes along geodesics. So let's take a look at an example of this on a 2D surface, the 2D surface of the moon. Let's say that we have two people standing on the moon's equator facing north, and both of them are going to walk straight forward along geodesics that point north. Because of the curvature of the moon's surface, these two people will naturally get closer and closer together until they meet each other at the North Pole. And if we imagine a circle sitting between them, this circle will get smaller and smaller as they each move farther and farther along their geodesics. So in some sense, the change of the size of this circle, given by the Ricci tensor, represents how quickly these two people get drawn together. And this is why the Ricci tensor represents gravity in general relativity, as we can see here in the Einstein field equations. The more space-time is curved, the more quickly bodies will get drawn together. So in general relativity, gravitational attraction is just the natural result of curved space-time. It doesn't require any forces like we see with Newtonian gravity. Now, the Ricci scalar keeps track of how the size of a ball in curved space deviates from the standard size of a ball in flat space. Now, when we're thinking in two dimensions, a two-dimensional ball is basically a circle. So if we were thinking of a plane in two-dimensional flat space, a two-dimensional ball would basically be a circle in this flat space. So thinking in two-dimensional flat space, if we took this circle, the area of this circle would be given by the blue colored portion on the inside, and this is the standard flat circle. Now, if we were to live in curved space, say living on a giant sphere like the moon or a planet, we could also draw a circle with the exact same circumference. So this circle in flat space and this circle in curved space have the exact same perimeter. But if we were to look at this circle in curved space and ask what its area is, we'd get this entire blue region here, which is sort of like an upside-down bowl that sits on the sphere like a cap. And the area of this cap in curved space is actually larger than the area here in flat space. So even though these circles have the exact same perimeter in both cases, the circle in curved space can fit more area inside it because of the nature of curved space. And the Ricci scalar helps us quantify how much more space we can fit inside this circle compared to the flat space circle. So through the power of curved space and the Ricci scalar, we can fit a lot more space inside a tiny boundary. And this is a phenomenon we often see in science fiction and fantasy. If we think about the TARDIS from Doctor Who, or Mary Poppins' magic bag, or that tent from Harry Potter, all of these things are bigger on the inside. And that's because all these characters are experts in differential geometry, and they know the power of curved space and the Ricci scalar. Okay, so we've looked at some visualizations, now let's look at some real math. There will be quite a number of mathematical concepts in this video, We're going to start with geodesic deviation, then talk about sectional curvature, then Ricci curvature, and finally we'll get to the Ricci tensor. So we're going to cover a lot of topics, but it will ultimately lead to the Ricci tensor. Recall that I use any of these three notations for basis vectors, and they all mean the same thing. And I'm hoping you recall from previous videos the formula for the Riemann tensor and also its components, which are computed using the connection coefficients. Now, recall that when we have a family of geodesic curves with a tangent velocity vector field v, we can also look at the separation vectors along these curves, which are given by the vector field s. And we showed that, starting with the standard definition of a geodesic, which is parallel transporting a vector along itself so that the covariant derivative of v in the direction of v is 0, we can take the covariant derivative again in the direction s on both sides, and then subtract and add this term. And here is the definition of the Riemann tensor when the Lie bracket is 0, and here we can swap the order of v and s using the torsion-free property. So we found that the second derivative of this separation vector s, which is also called the geodesic deviation, is given by the output of this Riemann tensor expression with a negative sign in front. Now I'm going to warn you about the sign convention here. In my videos, I'm going to say that the geodesic deviation is equal to the negative of the Riemann tensor of s and v acting on v. Or equivalently, we can swap the order of these inputs here and get the positive Riemann tensor of v and s acting on v. Some textbooks or articles might use the opposite sign convention, using the positive Riemann of s and v or the negative Riemann of v and s. Neither of these is more correct than the other. The negative sign is just a matter of convention. So I'm going to use this convention, but don't get tripped up if you see this version in other sources. It's just a different sign convention that they're using. So knowing this formula tells us how geodesics move relative to one another. So what would the geodesic deviation be in this case, where the geodesic curves are both traveling straight upwards like this? If we were to look at the separation vector s at various points, we would see that the separation vectors are all the same size. So this means that the second derivative of s is 0. So there's no geodesic deviation, and the geodesics aren't moving relative to each other. Now, what about a situation like this, where the geodesics are accelerating toward each other? This would mean that the separation vectors are getting smaller and smaller. In other words, the second derivative of the separation vectors would point to the left, in the opposite direction of the s vectors themselves. Right? If the s vectors are getting smaller and smaller pointing to the right, that's the same thing as the vectors accelerating towards the left. So because the s vector and the geodesic deviation vector point in opposite directions, that means that their dot product will be negative. And since the geodesic deviation vector is equal to the negative of this Riemann tensor here, that means that the dot product of the Riemann term and the s vector is positive. And again, this is when geodesics accelerate toward each other. Now, in this other case, the geodesics are accelerating apart, meaning the separation s vectors are getting bigger and bigger. This means that the acceleration of the s vector points toward the right, because the s vectors are getting larger and larger pointing towards the right. This means that the geodesic deviation vector dotted with the s vector is positive, or in other words, the Riemann term dotted with the s vector is negative. Now you might be asking why I'm using the second derivative of the separation vector instead of the first derivative. And the answer is that it's possible for geodesics in flat space, which are straight lines, to spread apart at a constant rate, meaning the first derivative of s is non-zero. However, the second derivative of s will always be 0 for geodesics in flat space. In curved space, geodesics can accelerate toward each other or accelerate apart, so the second derivative can be non-zero. So we use the second derivative to detect geodesic spreading because it will tell us about the spreading due to the curvature of space, and not the spreading that could happen in flat space because the geodesics are angled in specific directions. So looking at this dot product here, the sign of this dot product is very important. If it's negative, the geodesics are splitting apart. If it's positive, then the geodesics are converging towards each other. And if it's zero, the geodesics aren't spreading at all. So again, the sign of this dot product is important because it tells us if geodesics are converging or diverging. However, the size of this dot product depends on our choice of S and V. It would be nice if we could normalize this result so that it doesn't depend on our choice of the S and V vectors. And I'm going to tell you now that if we take this term and divide by the square of the area of the parallelogram formed by S and V, then the result no longer depends on the size of the S and V vectors. It only depends on the choice of plane that S and V live in. So now I'll cover how we get the area of the parallelogram formed by S and V. When we first learn the area of a parallelogram, we're usually taught that it's base times height, or in other words, the length of U, which is the base, times the length of W times sine theta, which is the height. This is also the same thing as the magnitude of the cross product of U and W. If we were to take the square of this area formula, we'd get the magnitude of U squared times the magnitude of W squared times sine squared. But as we know, sine squared is also equal to 1 minus cosine squared. And expanding it, we get these two terms. Now the magnitude of U squared is just U dot U, and the magnitude of W squared is just W dot W. And this entire term with the cosine is just equal to U dot W all squared, by the well-known dot product formula involving cosine. So this formula here is really the square of the area of the parallelogram spanned by U and W. So now that we've discovered this formula, we now know the formula for the square of the area of the parallelogram formed by S and V. So this normalized formula doesn't depend on our choice of the S and V vectors. It only depends on the plane that S and V live in. In other words, if we use this formula on the vectors U and W, which live in this orange plane, and then evaluated the formula on another two vectors, R and T, which are linear combinations of U and W, and therefore live in the same orange plane, the results of these two formulas would be equal. This is because when we change the vector U to AU plus BW, and change W to CU plus DW, this formula gets a factor of AD minus BC squared in both the numerator and the denominator, and these cancel out, leaving the result of the formula the same. I'll go ahead and prove this now, starting with the numerator. So recall that since tensors are multilinear maps, we can either scale the input or the output and get the same result, and we can either add the inputs or add the outputs and get the same result. When we start with the Riemann tensor of U and W, and then change to a new pair of vectors in the same plane, we can use multilinearity to split this sum in the first input into two terms. Then we split these sums in the second input into two terms each. Then we use multilinearity to put all these scalars out in front. Then, using the property of swapping the U and W inputs to get a negative sign, we know that R of U and U and R of W and W go to 0, since when a number equals the negative of itself, it must be 0. Finally, we can swap the U and W vectors here and get a negative sign, so we find changing the vectors in the plane gives us a factor of AD minus BC out in front. Now let's look at these other inputs of Riemann. If we apply Riemann of two vectors to a dot product like this, we learned in video 23 that we can use the product rule to get a sum of two dot products like this. We also learned that the Riemann tensor of two vectors acting on a scalar equals 0, since the covariant derivative of a scalar is just the partial derivative. So we get the Lie bracket minus the Lie bracket, which is 0. So this tells us that when we have the u and w vectors arranged like this with a dot product, we can swap them and get a negative sign. So when we start with this and then change to two new vectors in the plane, we can split this sum into two terms using multilinearity. And we can split these sums into two terms each using multilinearity of the dot product, and that will give us 4 terms. And recalling this property where swapping these two inputs gives us a negative sign, we know the terms containing two u's and two w's go to 0. And taking the scalars out in front, we get this, and swapping these to get a negative sign gives us a factor of AD minus BC once again. So this Riemann term with UWWU, when we change to two new vectors in the same plane, we get two factors of AD minus BC out in front, one from this UW pair and one from this WU pair. So now we know where this term comes from in the numerator. Now let's see how we get the same factor out in front from the denominator. Now one option for the proof is to just plug in all the A's and B's and C's and D's and just do a ton of algebra crunching to get the result, but that method kind of sucks. Instead, I'm going to cheat a little and rewrite these dot products as a cross product, since both are perfectly good formulas for the area of the parallelogram formed by U and W. You might criticize this approach and tell me that the cross product only works in 3 dimensions, so this wouldn't work in 4-dimensional spacetime, but this isn't too important since the result we get doesn't depend on the 3rd dimension anyway, since we're taking the magnitude. So starting with this cross product, we can change the vectors and then distribute out over the cross product to get 4 terms. Then we pull the scalars out in front, and then send these terms to 0 since a vector crossed with itself gives 0. Then swap these two vectors to get a negative sign, and then we see that we get AD minus BC out in front with a square. So this explains where the denominator term comes from and proves that this formula only depends on the plane containing U and W, not on the actual vectors themselves. And this finally brings us to our definition of the sectional curvature, which we denote by K of S and V. The term in the numerator gives us the sign we need to determine how the geodesics traveling in direction V are either converging or diverging. Either 0 when the geodesics are not separating, positive when the geodesics are converging, or negative when the geodesics are spreading apart. The term in the denominator is a normalization factor that keeps the result the same regardless of the length of S and V. This way, the sectional curvature only depends on the plane that contains S and V. Now, this is the definition of the sectional curvature, but I'm now going to talk about a related concept called the Ricci curvature. The Ricci curvature involves taking an orthonormal basis of vectors E1, E2, all the way to En, and then selecting a direction vector V, which is equal to the last basis vector, En. We say that the Ricci curvature in the direction vector V, denoted here, is equal to the sum of all sectional curvatures along every other basis vector direction. So in some sense, the Ricci curvature in some direction V is like an average of all possible sectional curvatures containing the vector V. So this might be a little bit hard to visualize, so let's look at some examples with pictures. Let's imagine a situation where all the geodesics are straight lines, and therefore all the sectional curvatures are 0. Since all the sectional curvatures are 0, this means that their average, the Ricci curvature, is also 0. So when a ball travels along these geodesics in the direction V, we just get a ball of the exact same volume, moved slightly to the right. Now, if this is our coordinate system here, there are two sectional curvatures that we need to worry about. The sectional curvature of V and the E1 basis vector has to be 0, because the separation between these geodesics is constant. They're not converging or diverging. Similarly, the sectional curvature involving V and the E2 basis vector is also 0, because these geodesics are not diverging or converging. So since all these sectional curvatures are 0, that means that their sum, the Ricci curvature, is also 0. So this would be an example of visualizing a situation where the Ricci curvature is 0. Now let's take a situation where all the geodesics are converging towards each other. So this means a situation where all the sectional curvatures are positive. If we look at the sectional curvature of V and E1, the geodesics are converging, so it's positive. Also, the sectional curvature of V and E2 involves converging geodesics, so the sectional curvature is also positive. And adding these two positive sectional curvatures together will give us a Ricci curvature that is also positive. So this is an example of a situation where Ricci curvature is positive. In this case, the ball moving along these geodesics will shrink in volume because the geodesics are converging. So positive Ricci curvature means that the ball will shrink in volume. Now let's consider the situation of geodesics spreading apart. So the sectional curvatures are negative. Again, the sectional curvature of V and E1 is negative because these geodesics are separating, and the sectional curvature of V and E2 is negative since these geodesics are separating. And when we add these two negative sectional curvatures together, the total, which is the Ricci curvature, is also negative. So this is an example of a situation with a negative Ricci curvature, and we can see that the ball moving along these geodesics increases in volume because the geodesics are spreading apart. Finally, let's take a look at an interesting case where some geodesics are diverging and some geodesics are converging. So in this case, the top and bottom geodesics on the ball are spreading apart, and the geodesics on either side of the ball are converging together. So the sectional curvature of V and E1 is negative because these geodesics are spreading apart. But the sectional curvature of V and E2 is positive because the geodesics here are converging together. And it turns out in this case, if we add the negative sectional curvature for E1 with the positive sectional curvature for E2, they end up canceling out perfectly, giving us 0. So this is another situation where the Ricci curvature is 0. Note that when the Ricci curvature is 0, the ball can still change shape. What isn't changing is the ball's volume. When we move the ball along the geodesics, it will get squished from the sides, but the top and bottom will get pulled apart. And in this case, even though the ball is getting squashed and stretched, the volume hasn't actually changed. The compression along the sides and the stretching of the top and bottom cancel out exactly so that the volume of the ball doesn't change. And we can see this because when we add all these sectional curvatures together, the resulting Ricci curvature is 0, which means that the volume of the ball is not changing. So it's important to remember that the Ricci curvature can only tell us about volume changes. It can't tell us about whether or not a ball is changing shape. It will only tell us if the ball has changed in volume. So hopefully you can now visualize the idea of Ricci curvature. I'll now explain how this is related to the Ricci tensor. Let's write out the formula for Ricci curvature, which is the sum of all the sectional curvatures for an orthonormal basis, with the direction vector v being one of the basis vectors. So I'm not writing this explicitly, but there's a summation over I going on here. Since the basis is orthonormal, ei.ei equals 1, v.v equals 1, and ei.v equals 0, since all the ei's are orthogonal to v. This means that the denominator of the formula is always 1 for an orthonormal basis. Now let's expand the v vectors as linear combinations of the basis vectors. And since the Riemann tensor is a multilinear map, we can pull these scalars out in front. And this expression here just means the Riemann tensor component with lower indexes kij and upper index I. Since there's a summation, or contraction, over I, we can write this contracted Riemann tensor using this notation with two lower indexes. And these are the components of the Ricci tensor. They're the components of a tensor with two lower indexes that we get when we do this summation with the Riemann tensor involving the top index and the lower middle index. So when the Ricci tensor acts on the same vector twice, the result we get is the Ricci curvature. It's also important to note that the value of the Ricci curvature for a given vector is always the same and doesn't depend on the orthonormal basis that we choose. If we change to a new orthonormal basis using the forward matrix F, the resulting vector components of the vector v will transform using the backward matrix B, which is the inverse of F. This is because vector components are contravariant and transform in the opposite way that basis vectors do. And since F and B are inverses, when we sum them together, we get the Kronecker delta. The Riemann tensor components will transform using 3 covariant rules and 1 contravariant rule. So we get 3 F's and 1 B. And if we compute the Ricci curvature in the new basis and expand everything out, this B and this F cancel to a Kronecker delta, this B and this F cancel to a Kronecker delta, and this B and this F cancel to a Kronecker delta. And by the Kronecker delta cancellation rules, this becomes a K index, this becomes a J index, and this becomes a 1. So you can see that we get the same result we originally had, even though we're using a different orthonormal basis. So the answer doesn't depend on our choice of orthonormal basis. Finally, we'll look at a specific example of Ricci curvature. We'll look at the case of the sphere, which we've been looking at throughout this series in the U1 and U2 coordinates. There is only one independent non-zero component of the Riemann tensor, which is the 1, 2, 1, 2 component, and the metric tensor for the sphere is here, where the lowercase r is the sphere's radius. For the Ricci tensor, half the components go to 0, and the 2, 2 component can be read directly from the Riemann tensor. The 1, 1 component takes a little bit more work with raising and lowering the indexes using the metric tensor and using the Riemann tensor symmetry properties, but we can determine that it's equal to 1. So if we compute the Ricci curvature using the sphere's Ricci tensor, we find that we get a formula where all the terms are squared, which means the Ricci curvature must be positive. Positive Ricci curvature means the geodesics will always converge, which is what we would expect for the sphere, as we saw for the example of 2 people on the moon walking along geodesics that meet at the North Pole. So the sphere is a curved space where the Ricci curvature is positive everywhere, which means that geodesics will always converge. Now, this interpretation of the Ricci tensor is nice enough. However, it only makes sense when we're dealing with a basis that's orthonormal. I'd like to give another interpretation about how the Ricci tensor is about changing volumes. And this is an interpretation that works in any basis. And to do that, I'm going to have to talk about the idea of a volume element. Unfortunately, this video has gone on long enough, so I'm going to leave a link in the description to the next video where I'll continue talking about the interpretations of the Ricci tensor and Ricci scalar. As always, if you enjoy my videos and would like to leave a tip, you can check the description for a link to my donations page.